Good morning, everyone. Happy Friday. Welcome back, or welcome to, depending, the 2025 AAS Goddard Space Science Symposium. We're very happy to have you all here today. Thank you so much for coming out. My name is Jim Way. I'm the Executive Director of the American Astronautical Society. So thank you very, very much to all of our sponsors for this event. Your support makes it all happen. The Aerospace Corporation, BAE Systems, KBR, Johns Hopkins Applied Physics Laboratory, L3 Harris, Leidos, SAIC, and Northrop Grumman. Thank you to all of you for your tremendous support. Thank you to the entire team at the NASA Goddard Space Flight Center for everything you do in helping put this together. And I understand the tour went very well the other day, and so thank you for doing that for our folks. And thank you very much to our planning committee, a very wide and diverse set of people here that meet once a week for a few months to bring this all together. If anyone here is, interested in maybe participating in something like that, please let us know and we'll be happy to talk about it. Social media, we're on all the platforms, so please don't hesitate to talk about this event to your friends and colleagues and followers. We would appreciate it. And thank you very, very much to SAIC for sponsoring our breakfast and breaks today, as well as this first session. So to kick things off and to introduce this session, I'd like to welcome up Krista Peters-Ledard. She is the Director of the Sciences and Exploration Directorate at NASA Goddard, and she is our Planning Committee Co-Chair. Krista, thank you so much.
Great. All right. Well, thank you and welcome to day 3 of the Goddard Space Science Symposium. I'm so excited about today. First, I want to welcome all of you folks in heliophysics and space weather that just flew in from Boulder from Space Weather Week. So welcome. Glad you're going to be here today, because after this morning's panel, we're really going to focus on heliophysics and space weather. So that's, rounding out the day today. I also am excited about our luncheon speaker, Mark Clampin, who is going to be here, our acting deputy associate administrator. So we've got a great program for you today. And as we kick off the first panel, I just want to remind some of you, especially since some of you weren't here yesterday. Yesterday morning, we had a panel with Tom Wagner, right, the Earth Action Lead. And one of the things he talked about was how many Fortune 100 companies use NASA data. And they've been not only tracking it, they've been talking to folks. And so I think in this morning's panel, you're going to be able to hear a little bit about how NASA, NOAA, and other data sets are being used to advance the way we integrate data and advance our forecasting capabilities. So the opening panel, integrating multi-sector data to advance Earth and space science, with the moderator, David Maddox. Let me introduce David. He's a data engineer and strategist in SAIC's Innovation Factory. He's got a bachelor's in bioinformatics from BYU and MBA from Iowa, and 11 years of building data systems, including at a startup. He's a problem solver. He likes to bridge the gap between the technical side and the business side. And I think this panel is the perfect place to talk about that. So without further ado, let me turn it over to David and the panel and have the panel members come forward and join us on stage. Thank you.
All right, testing. Thank you for that introduction. I appreciate that. Yes, my name is David Maddox. As was mentioned, I'm a data engineer. And when I was first asked to moderate this panel, I thought, for the American Astronautical Society, thought, I am going to be the dumbest man in the room. This is, and they're still going to give me the microphone. I don't get it. But as we're talking about how this is about the data and the data science and the things we're doing with the data, it's like, okay, I'm in the right space. Thankfully, though, our panelists here all have quite a bit of experience using NASA and other data sets, astronautical data sets, for studying our science and doing really great things with them. So I'm excited to we're going to have each of them introduce themselves. And then there's a few slides. They'll present those, and then we're going to open it up for questions. And I'm really excited for that part. And so write your questions down as they come to you, and we'll hopefully get to all of them. And with that, we'll start with Joe. Joe, tell us about yourself.
All right, get this microphone on. Is this on? Yes. Yeah, so my name is Joe Munchak. I am a principal atmospheric data scientist at Tomorrow.io, which is a private company in the weather forecasting and intelligence realm. Prior to that, I was a physical scientist at NASA Goddard Space Flight Center for about 5 years. So this is very good to be back in Greenbelt to be at this symposium. I got my PhD from Colorado State University in 2010 and did a lot of work, both my PhD and at NASA, on satellite precipitation measurements. And that's work that I've carried into my current role as well, as you'll see from some of the material I have prepared. So very excited to be here. And I wanted to thank Krista for the invitation and to be on this panel.
Yeah, appreciate it. Awesome. Gray.
All right. Okay, my name's Gray Nearing, and I'm a scientist at Google. I also used to be at Goddard for about 4 or 5 years, back 2013, 17, I don't remember, a long time ago. I'm a hydrologist by training, so I'm a hydrologist at Google, and I work on flood forecasting. And more generally, I work in the climate AI sector of Google, which is a large section of Google research at this point is focused on climate AI. I do a little bit of work in the startup sector, mostly as an external advisor, not anything official. And I have a background also in academia. So between Goddard and my current role at Google, I was a professor at a couple universities. So, yep, that's me.
Awesome. Campbell.
Hey everybody, I'm Campbell Watson, IBM Research. So I'm based in New York. My background is as an atmospheric scientist. I joined IBM Research around 10 years ago and have since then been really focused on bringing AI into weather, climate, environmental, and now space problems. And just briefly, IBM Research is the longest standing industry-based research lab in the world. We have around 3,000 researchers across 12 labs. And one of our, obviously we have big efforts in quantum, hybrid cloud, and AI. And we have a team of around 70 folk across 6 research labs working on problems to do with climate and sustainability, including work with NASA. Thanks.
Thank you. Like I said, we've got a great panel here. Joe, I would like you to kick it off. I know you had a few things you wanted to share about NASA's investments in space, not just space flight, but space data.
Yeah, thanks, David. So I'm going to hopefully go pretty quickly here just to explain a little bit about what Tomorrow.io is and what we do and how we've benefited from NASA technology developments and science and scientific research in what we do operationally. So Tomorrow.io, like I mentioned, is a private company primarily focused on weather forecasting and solving problems for businesses, enterprises, and governments related to weather and climate resilience. We also are partnered with TomorrowNow.org, a nonprofit which extends a lot of these forecast efforts to other end users, getting that last mile information primarily through large scale philanthropies. If I can get to the next here. Okay. Okay, so right, it's a partnership, and I mentioned that because a lot of the applications that we do really are geared towards areas that don't have great weather observing infrastructure like we do in the United States and some other wealthy countries, and that's why the .org part is so important to what we do. Yeah, like I mentioned here, this is just Tomorrow.io in a nutshell. We have, I think we're now in our 9th year as a company. I've been there about for almost 4 of them. Very large customer base spread across different sectors, enterprise, government, the nonprofit and so on, many sectors within the enterprise, logistics, airlines, healthcare, just to name a few. Our technology is what differentiates us. We have the full stack from observations, and then I'll get into those satellite-based observations, to our own suite of models that we run internally, and then the platform which delivers the actual actionable insights and advice, distills that complex modeling into pretty much a yes or no decision at the customer level based on their particular criteria for what needs to be done in relation to weather. So this is, that just chain in a nutshell. So again, observations to modeling to this scalable, what we call as software as a service platform, and AI is being integrated through all these steps. Okay, so what we believe differentiates us in particular is that observations are the key. And this, I think to a NASA audience, this should come as no surprise. NASA has pioneered satellite observations for many aspects of weather observing. A lot of those get operationalized by NOAA eventually. I think some of them we've taken more directly and operationalized ourselves through technology transfers. So models, everyone's got an AI model, right? If you read any of the news, everyone's got AI forecasting models. These are mostly open source. So in some sense, they're becoming a commodity. Certainly a lot of architectures are being developed at a very rapid pace. And I'm sure that my co-panelists here will have much more to say about the advances that are being done there. But the models ultimately depend on good data to feed them. And that's, I think, where we try to differentiate ourselves by taking observations that provide us information that you can't get anywhere else. So how do we do that? We do that through our innovative satellite constellation. And so this consists of 2 flavors of instruments. We have Ka-band radars, so we're actual weather radars in space, the first private company to do that. And we have a constellation of microwave sounders, which we already have 6 on orbit. We just launched 2 of them last week. And so those are in the early stages of commissioning, and we're going to be getting science data. So that's, when I get back to the office, what I'll be looking at is some of the first light imagery from those. That's a very exciting part of my job that I really enjoy. So these are our impactful measurements because they, in many ways, complement the measurements that are taken by agencies like NOAA, NASA, UMetSat. The radars is still a fairly novel measurement from space. NASA, of course, pioneered this with TRMM and GPM along with JAXA. And then we also have the cloud radars, CloudSat and EarthCare as well. And these are still very much research grade radars. They're not intended for rapid revisit operational use just because of the narrow swath. It's just a fundamental limitation. It's a great observation. It's highly impactful, extremely detailed and unique, but too costly to do at scale. And so that's what we're trying to do, is miniaturize it and scale it up to where it can become as ubiquitous as some of these other modes of measurement. At the same time, we're expanding our microwave sounder constellation. So microwave sounders are consistently shown as the most impactful measurement on numerical weather prediction skill. And so the more of them you can get, you're going to improve that skill. That's technology was miniaturized through NASA, as I'll show, and we've taken the technology transfer and are scaling that up as well. And it's also very useful for the precipitation nowcast. So our radars, this is just a quick info sheet on our Pathfinder radars. Like I said, these were intended to prove the technology in space that can be miniaturized and done at low cost with the Ka-band radar backend. This, the actual backend we're using, while it's inspired by the GPM and NASA JAXA missions, this is actually has more heritage in some NASA airborne instruments, such as HIRAP. But we put it in space, hardened it, raised its TRL, and we've been collecting observations for a couple of years now from these Pathfinder radars. And actually, some of this data is being procured by NASA with its commercial smallsat data program. So we're really excited to see the research that can be done and more new applications that can be found from this radar. So we're extremely, I think, excited to be part of that program. And that's still in the early stages, but we're already getting great feedback on these instruments. The microwave sounders is perhaps a more direct technology transfer because this originated in the NASA Tropics mission. And we essentially built the next iteration of Tropics with many of the original investigators from MIT Lincoln Laboratory. And this is something that we're in the rapid scaling deployment phase right now. We have, I mentioned, 6 on orbit. This is data from our first 4 back in January, and that I'm showing here on that animation, but we're continuing to scale it up. We'll have a dozen or more by the end of the year, and continuing plans already for a 2nd generation instrument with even more capabilities. So how does it impact our end users, right? It's great that we're collecting data, but we have to, perform the modeling, data assimilation, and ultimately getting that info out to the users. So this is an example of our unified precipitation product. So if you're familiar with the NASA GPM program, you probably know about iMerge, which is the global merge product. So this is our real-time version of iMerge. It leans on a lot of both public sources and our own satellites, and we really couldn't perform the best analysis without both. That's the key message here. So we have the ground radars, which are great where you have them. That's what you see on the left panel. But there's huge, areas of over oceans, over countries that don't have ground radar networks. So what do we do there? We have to use satellites. And satellites, we always have geostationary. That's the backbone of the measurement. And AI can do pretty well with geostationary, but the microwave is still a more direct measurement. Our Pathfinder radars are an even more direct measurement. And so we have a technique that blends all of those together to get you the image on the right, which is a seamless transition from where you have ground radar to where you don't. We've shown, and again, I said, we know that our own satellites offer us some advantage with the revisit rate and low cost observations, but we still can't have the best impact without using the publicly available data too. So GMI is also an input. GMI on the GPM mission is incredibly, I guess, robust instrument, very well calibrated, great resolution. The data comes from it with some of the lowest latency you get from a NASA mission. Usually it's in under 30 minutes. And that just makes it incredibly valuable for us. We get twice the impact from GMI as we do our own satellites. Now, there's only one GMI and we're launching a dozen or more. So there's a trade-off there. But I think this shows, again, the benefit of these multi-sector data sources, which is the theme of this panel. Our own satellites also have that impact. So if you see on this chart shows Hurricane Milton passing over Florida. And you can see when we have an overpass, we get a bump in skill when we add in our own data on top of the public sources. That's how we differentiate ourselves. Again, by having these satellites that give us that bump in skill over what you get from the geosats. Okay, so I think I'll move on to the next panelist.
Well, yeah.
Now
Let me ask. So I actually got a question. So, in getting all these data sets together, are you finding that you have more of a technical or administrative problem getting your data together?
At this point, it's more of a technical problem. The public data is out there. We have people that are just absolute geniuses at data engineering and can pull data from everywhere, get it into the formats and do it quickly with cloud computing and at scale. So once, that problem's solved, it's really just a matter of building the pipelines and making them operationally robust.
Yeah, very cool. Well, thank you. That's fascinating. Great. Tell us a little bit more about what you're doing at Google.
Cool. So I think I'm going to skip most of the slides and just kind of talk about what we're doing. So what we're doing at Google Research really is building AI models. So I'll just give a sense of why we're doing this in the space of, let's say, Earth observing climate science. And there are really 2 reasons. One is because people come to Google for information, and we want to be able to provide that information. So sometimes, although unfortunately not today, my slide deck has a picture of the Google search bar with a bunch of suggestions, and you type, is it flooding in? And it'll say, is it flooding in, California or Nairobi or something like that. And people just come to Google for information. So we started trying to collect this type of information, weather data, natural hazard data, data about things that are usually provided by governments. We started trying to collect that information directly from governments. This was an effort within Google called Crisis Response. The challenge is that it just wasn't reliable. Most governments were not able to provide us the information that our users were looking for in a timely enough manner. So we started exploring the options around building our own models. And this has this has some benefits. Like we can build models that predict floods. I particularly work on floods. We can predict floods. We can track wildfires. We tried earthquakes for a while. That didn't work out so well. And now, of course, we have everybody probably knows about Google's weather forecast. We just saw GraphCast listed earlier. GraphCast is now being disseminated by the European Center for Medium Range Weather Forecasting, the main EU weather forecasting service. ECMWF has just built their their AI forecast system, which is modeled heavily on GraphCast. So we've started building these models that help us provide better information to people. That comes with an additional benefit, which is our second reason for doing this, which is that Google is always just looking for problems to work on within Google Research. So this is I'm in Google Research. We're always looking for AI problems to work on. Google Research really cares about producing basic AI science. These are things like TensorFlow and transformers, the tensor processing units that you can rent on Google Cloud to do neural networks faster. But these kind of basic, innovations that really make a huge impact in the world can only happen if there are practical problems to work on. So Google is always looking for practical problems to work on, these things around education, health, climate, now, of course, LLMs. So this kind of just keeps the cycle of research going. And it also, especially in the sort of climate AI sector, helps provide information to users. So we don't necessarily produce data. That's not completely true. I think maybe yesterday or 2 days ago, Google.org helped launch a satellite with Muon Space called FireSat, which is helping to track wildfire boundaries. But for the most part, we build AI models and we use data. So I'll just give a couple of examples of what that looks like. Come back to this. So, the main problem that Google has is we're a global company and data are not equally distributed around the world. So we're trying to solve this problem of how to get people reliable information in all types of data paradigms. And so this is an example from the flood forecasting project where we look at the total amount of open public river data in different countries, and we correlate that with GDP. And what's hidden under this graph, which in many audiences I take as a background knowledge or a given, is that there's a direct correlation between the GDP of a country and the vulnerability of a population in a country to the human impacts of flooding. So where flood forecasts are needed the most. And we kind of see that there's this inverse correlation of data availability to produce the types of forecasts that people need and the direct need for those forecasts. So the way that we tackle this problem, and this is sort of emblematic of our approach across the climate AI sector at Google, is we take all of the data that we can possibly get and we train a model on all that data, and we hope that that's enough for the models to learn how to generalize. So this is the data set that we use to train our flood forecasting model. Each of these little points is on a river somewhere in the world, and all of the white space is where we don't have data and where we want a model that's been trained on all the data available to make good predictions. And collecting all the data really has a bunch of challenges. It's a process of going out into the world and asking everybody for the data that they have available and then bringing that in. That's satellite data, that's weather forecasts from every agency that we can get weather forecasts from. And it's ground truth data, which we'll come back to in just a second. For floods, that's stream flow, inundation maps, impact analyses from the Red Cross, disaster data sets from the United Nations. These types of things are all different types of data that we use either as inputs or targets for our models. And then we do the AI work of understanding how to build AI models that are able to synthesize all this data in a useful and interesting way. And so here's just one example of that, where we're using transformer embedding layers to deal with missing data. So there might be really good weather forecasts from national governments around the world, or there might be satellites that follow an orbit. So we get some data all the time, but not data everywhere all the time. And so we have a lot of missing data problems. And this is just one example of how we deal with that by building, transformers that can kind of pay attention to the data input channels that are active at any given time, and then use those to make predictions. We have a whole bunch of ways to do that. The main problem that we have is that there's no such thing as ground truth for like 90% of the things that we do. there's scale mismatches between the most accurate data and the human impacts. So there's, it's not the case that humans are affected by how much water is in a river. It's the case that humans are impacted by when a river overflows, but we can only measure how much water is in a river. So there's no real ground truth for flooding. The same thing is true for soil moisture, which is just a very basic physical variable, and that's what we're looking at on this plot. We can get really accurate measurements at the centimeter scale. There are data products that are valid over large areas, and soil moisture is critical for drought forecasting. So we do provide drought forecasts to the World Food Program and to the Red Cross and other aid organizations like that. We have a drought forecast model that's running, and soil moisture is one of these. And so what we try to do is we try to collect information from everywhere we can get it. We collect it from models that other groups run. We collect it from satellites. In this case, it'll be SMAP and MODIS satellites that we get our data from. And we also get data from global in situ monitoring networks. And most of that, incidentally, also comes from NASA. A lot of that comes from the SMAP CalVal program that happened 10 or 15 years ago. And we're still getting our best data from that. And we get, as we add all of these different data sets to our model, we get slightly better predictions, and these turn into slightly better, seasonal forecasts of drought, and we feed that into some food security models and some economic models as well. There's so one of the things that has been happening over the last few years in terms of building AI models for geoscience problems is we've made a lot of progress. There's been a lot of changes in what's happening in AI geoscience. A long time ago, and I'm talking like 2015, back in the ancient eras, we were doing everything with concept models. We were trying to solve physics equations, and then we started to learn how to bring in these learning technologies into the problem. And these learning technologies are really what allow us to capitalize on the wealth of data that's out there. They allow us to bring in data from anywhere, even if we don't explicitly have the physics equation to make the relationship between that data product and what we want to predict. We can still harvest information from those data products. And so the geoscience community has gone through sort of phases of relaxing the data requirements. So needing, not necessarily needing retrieval models, but actually just working on the spectral bands from the satellites that are being launched. This is really, really valuable, and we can learn a lot from this. But also on the target data side, now we're able to bring in disaster data sets as explicit targets. So for an example, for flash floods, one of our main training data sets are the alerts coming out of NOAA. So we harvest the whole history of alerts that NOAA has ever produced for flash floods, and we use this as some of the training data for our model. Also, some of the impact data sets from the Red Cross and the United Nations we're using in the same way. But now what we're talking about is these things called geofoundation models. I'm kind of using this word in my own way to mean models that aren't necessarily built for a specific purpose. They just take all the data and they create embedding spaces for this data. So it's not like we take input data and target data and we say, I'm going to use this set of data to predict this set of data. Now we're able to develop technologies that just see, theoretically, although no one in our company is there yet. I don't want to speak for other companies, but theoretically see all of the data in the world and then learn representations of that data that then can be useful for any application that you might want. So you might have a geofoundation model built on weather forecasts and remote sensing that's used for wildfire prediction, flood prediction, and food security, agricultural products, drought prediction, all these types of things. So that's where we're at right now. Thanks.
That's really cool. Yeah. So we've had this conversation before, but I work with a lot of data scientists, and our problem as we work with the government, problem is rarely the AI side, it's the data. We just don't have enough data. Yeah, I can feel your pain, and I think that's really awesome what you're pushing for. One of the things you mentioned were foundation models. Campbell, can you tell us about some of the work you're doing at IBM and how foundation models can help further fill the gap where we are missing data, and getting all that data is, you guys are doing a great job tomorrow.io, but there's just still so much data we could use to get more precision out of our models. So tell us a little more about your foundation models and the work you're doing at IBM.
Thanks. I'll begin with, I think, the genesis of our relationship with NASA, at least my group. Obviously,
Sure.
IBM's worked with NASA for decades, including the moon landing technology. But our group started in around early 2023 with interactions with the impact group down at Marshall, who are interested in looking at scientific literature with language models. And so taking a kind of a large language model type approach. That work was underway, and we started to think about, well, what if we took this similar approach of unsupervised learning on a large corpus of data and used it with Earth observation data? And the one that jumped out was the HLS data set. It's well curated, high quality control, global coverage. Can we build a model that learns a sort of a general representation of that data? So just like Gray was saying, this geo foundation model. The idea is that you can do all this work upfront to train a model that kind of understands what HLS data looks like, the correlations between pixels across space and also across time to a degree. So we built that model, we released it open source, and there was a tremendous reception to it. It was called Prithvi. This is version 1. And from that, we embarked on a process of, well, what other domains should we be building foundation models for? And so we started to build a foundation model for weather and climate using the MERA-2 dataset, and that has also been released. And I think it's when we started to work in the weather space with this weather data that we were frequently asked, well, are you building a weather forecasting model? The answer is no. We're building a foundation model that knows about something to do with the dynamics of the atmosphere. The idea is that you build this one large model that can then be adapted to a range of downstream tasks because it kind of knows stuff about what's happening in the atmosphere or happening on the land surface if you're using Earth observation data. So if we step back to the HLS data, there's a range of downstream tasks that one would use satellite data for. In this case, this optical data. Flood detection, burn scar detection, landslide detection, things around forest monitoring. Traditionally, one would take that satellite data, train a model to predict a specific task, such as flood detection. But in this case, we thought, why not do all that work up front to understand, have this, what we call this embedded space, this embedding space that has a general representation of HLS data. And then it's a small amount of effort to fine tune that model, to do flood detection, to do above ground biomass estimation, so on and so forth. And so we applied that to the weather paradigm as well. We don't want to have a model that is only doing forecasting. We want one that can also do downscaling, that can also do detection of extreme events in climate model simulation data. And we use it, for example, looking at what if scenario analysis for extreme events, say hurricane track trajectory. When we moved into the weather and climate domain, there's obviously atmospheric physics and dynamics is really important. Does this model respect physics? I think unlike in the Earth observation domain, physical relationships between what you see can be a little less well defined. In the atmosphere, we have equations that can model a lot of this. And so we embarked on a process of starting to examine what the model is actually learning when it's exposed to a huge amount of, in this case, MERA-2 data. And we found that, for example, it did a relatively good job at respecting, say, conservation of momentum, and other conservation laws, especially around water. We, for example, ran an experiment with what if we add a thermal perturbation in the middle of the atmosphere in this location? How does the model respond? Does it become does the perturbation lead to some instability in the model? Then we end up with something entirely unrealistic, or does it do what we would expect a numerical weather prediction model to do? So these are the types of experiments that we've done. That paper is going to be coming out soon, and we were very encouraged by what the model could do. So the impact group at Marshall that we work with, their focus is not just Earth. Their focus is providing tools, technologies, and libraries for all the scientific divisions across NASA. And so we've started to build a foundation model for heliophysics. This is using the SDO data. We're beginning to scope a foundation model for the moon, so lunar. So this is using the the LRO data. And we have intentions of broadening this. In parallel, we're revisiting what it means to work with scientific literature with the intention of trying to speed up the research workflow. Ultimately, we see this as one big picture. You have knowledge, say in scientific literature or elsewhere. You have models, these foundation models that we're building. There's some sort of layer in which a user interacts with all this, and then there's data sets. And so the ultimate vision is to try and build tooling that allows users to extract knowledge, form hypotheses, then have what we call agents to go and run experiments that are formed, all human in the loop, accessing the vast amounts of data that NASA is generating and others. So that's sort of like that is the bigger vision that we're going for. One of the reasons IBM is particularly interested in this is that there's a huge focus on large language models at the moment. So language is the modality, but there are other modalities that are interesting. And this multi-modality is really, you see it now with language and images. So vision language models is an area of a lot of great exploration at the moment. Geospatial information, space information, it's a little bit like vision, like pictures, cats and dogs, but also not. It's also more complex. And it's a great representation of scientific data, which is complicated to work with. And so what are the tools that are needed to work with this data that can really speed it up? We're committed to open source. So a lot of the tooling that we build to use these models, to make them more usable, more consumable, more user-friendly, are being open source. So an example is a library called TerraTorch that is designed to take geospatial foundation models that have been developed by us, also developed by others in the community. I think currently there's 75 individual foundation models for Earth observations that have been developed and released by the broader research community. And so we have an open source tool that can take many of these foundation models and then help you adapt them to the task you're interested in. There's a benchmarking framework that goes along with it, because we're committed to trying to make sure that there's systematic ways of understanding which models are good for which types of tasks. And what we're finding through interaction, especially with domain scientists, let's say in the land surface field, could be a scientist that's interested in detecting cocoa plantations across Africa. Can be a really tricky problem because sometimes they're shaded cocoa and the observations might be single dot points. This isn't necessarily an easy data set to work with when you have nicely curated HLS data. So what are the tools that are needed to bring these types of data sets in and allow users to tackle these problems and make the most of the huge amount of work that's gone into building these foundation models? I think another thing I want to touch on is this concept of multimodality. So the foundation models I mentioned, we trained a model with HLS data, trained a model with MERA2 data. We're training it with the SDO data. These are in essence, unimodal. It's just optical multispectral data in the case of HLS. If we look at, for example, commercial satellite data, it's not quite like HLS. It can be a totally different resolution. You could have, say, Sentinel-1 data. So this is radar data, again, a different modality. So we're exploring ways in which we can have a foundation model that works with multimodal geospatial data. We have a big presence in Europe, and so we've been working with the European Space Agency, and we've developed a model that will be open source soon. The paper's going through review, called TerraMind. And what this does is it takes Sentinel-2, Sentinel-1, land use land cover maps, digital elevation, and a few other modalities, and it fuses them together in a way that was pioneered, I think, originally in the autonomous vehicle space. And this, we think, is sort of the first multimodal geospatial foundation model that will be released and serves as a blueprint for how it is that we can fuse in information that has different resolutions, different modalities, with very different information. I think that there's still quite a lot of work to do. The concept, I think I heard the other day that NASA has 11,000 different data sets. I do not think there's going to be a foundation model that works with all 11,000 data sets. But of that 11,000, there's roughly 500 or so that are highly used. I don't think we'll get there with the 500 or so data sets either, but there may well be a suite of these foundation models that work with sets with these data sets. And on top of that, providing the tooling that allows the easy customization to data sets that aren't natively supported. I think that is a really key part. So I can leave it at that.
Yeah, no, I appreciate that. That's really awesome. I love the, as many of you know, in traditional or early days of machine learning, you had basic predictors where you had a bunch of data that said these were the conditions and this was the outcome, and you could just feed that to your model and train a model and it would predict something for you. Again, as we've noted, that data is just not available. So we have a lot of things that we have to, we have a lot of techniques to get around that. And
Right.
thankfully the data is becoming more available, thanks to the good work of a lot of the people in this room, actually. But being able to, thinking about it as a sort of an LLM for science, these foundational models, just really open up the ability to study what's going on with the relatively limited amount of time or data we have. So
I think, can I just add
Please.
one more thing regarding foundation models? I think one of the reasons that some people get excited by it is that once this model's been built, when you're adapting it, you typically need less data to adapt it to your given task. So if we just take flood detections as a straightforward one, there's only so many floods that have been detected from space and labeled by hand. So you have a high quality labeled data set. A foundation model means you need less of this labeled data set to come up with a good prediction model. So this is a really attractive concept for example, we go back to detecting cocoa plantations. There's only a certain amount of high quality data out there in which you can train your model. Or if you're trying to detect illegal mining in the Amazon, another good example where there's just a handful of examples. And so having this model that understands something already about the data in which you're using to make the prediction is a really useful head start.
Yeah.
And also kind of makes the process of building these models more uniform, which should help with transferability across groups.
it's like a giant Bayesian prior.
Sure.
Awesome. This is great. With the remaining time we have, we'd love to open this up to questions. So I hope you have, we've got some questions out there, and I think we have a few microphones. All right. We can hear you. It's always the first time we use the microphones. This is what happens. Yeah, it's good.
So you've all touched in different ways on the whole benchmark data set, right? And that being the public good. So I wondered if you could comment in different roles about what the role and the values of these data sets, the authoritative, industry competitive space, and the data sets that match their will provide. You know, we talk about the benchmarks comparing to independent satellite measurements, we talk about the foundational models, but I think that we kind of take it for granted that these authoritative data sets all do there. And I'm curious how you see value of having this public data set at your disposal for LLMs or satellite calibration. So curious.
Actually, kind of summarize the question for our folks.
Yeah, certainly. That's a great question. And I hope I can do that justice in that summary. How has the existence of the public data set, this sort of common good, made an impact on the LLMs and the data science that we're doing now, and how important will that be going forward? Hopefully that's an okay summary.
Yeah.
Joe, go ahead.
Yeah, so it's a very, very good question and very relevant to the work that I do, because we're trying to produce, again, scaled commercial satellite measurements that have a proven quality. And the benchmark we always go back to is the NASA data. So in the case of our microwave sounders, we compare the measurements to GMI because we know GMI is the gold standard for calibration in this particular sensing modality. And so it's great that we have that resource, and it builds a lot of trust, for our customer base if we can point to that benchmark. And so that's incredibly important. And it's not something that we can do. And if we could, that we don't have the trust that NASA has in their brand, to be honest. So I think that having that trustworthy, well-known quantity and benchmark is incredibly important for the type of work that we do.
Those are great points. Any comments, Gray?
Yeah, so I think my answer would also be around the trust question. So everything that we do in my particular team, I don't want to speak for all of my company, it's way too big for me to speak for, but is open and public and designed to be interactive with governments, both at the international government level and the national government level around the world. And so everything we do has to be open and public and preferably reproducible. So, and that's because otherwise there's a trust barrier with the people that need this information. And so having having these open and public data sets is really the linchpin of being able to do the kinds of things that we do in our private company that has a benefit for the public. This is still a really difficult question. What's the role of private government in the space of hazard alerting? It's a very, very difficult and important question. But the fact that we can do everything that we're able to do with open and public data is really, really critical. I'll leave it at that.
I like that word authoritative. I think I'll touch on two words here. So authoritative, I'll come back to. Trustworthiness is critical. And this is especially so in the large language model space. So there's a huge amount of effort placed on governance. So making sure that the data that the model is learning on, bias, etc., but also making sure it's not copyrighted is another thing that needs to be accounted for. And so what we don't really have in the large language modeling space is a data set provided by an organization like NASA, which says, these are the terms of use, and this is the quality commitment that we provide. So for our group, it's amazing having a data set, having the data sets that NASA provides, because terms of use are open and it's also authoritative. There's certain amounts of, there's quality control that's put in place. We are often asked, we want to use your foundation model with, for example, planet data. Yes, it can be used with planet data. It can be adapted to take high resolution optical data. Working with that data is a different story, in part because there can be challenges with geo-registration, return visits, etc., etc. That is often overlooked when we're working with NASA data, which is such a lovely thing for us. So I hope you sort of get the sense that there's equivalence in the large language modeling space and the geospatial foundation model space, but I think for different reasons.
That's excellent. I would just point out, so as they were mentioning, having that data available is, again, gives a lot of authoritative, allows people to validate what's being done. In our conversations earlier, we noticed a lot of the proprietary data, or we mentioned a lot of the proprietary data is higher resolution at times than the NASA data, and that's fine. Again, having the NASA data allows us to build that framework at the beginning, so that proprietary data with its high resolution, we can get so much more out of it, which we would not be able to do without data sets. All right, that's a great question. Thank you. All right.
Thank you for the great talks. I'm Oreste Reales, SAI, work at Goddard. So my question is focused on weather forecast. And one of the aspects that we noted that there is the tendency of present AI-based model against the physically based model as somehow competing with each other, which I don't think is a great idea. What ECMWF has revealed in their study with their AI-driven models is that the skill of the model that is completely AI is extremely good when events that are being predicted are within the training. However, when there is some event that is outside the training, because of course we have some event that have 100-year or 1,000-year kind of possibility of repeating themselves, the skill goes down. So the question that I have for all of you, how do you think, the intuition would be that we should always keep both types of predictions, so physically based and AI based and complementing each other. I feel a little worried about the idea of having a completely AI-based models for weather forecasting. One aspect in the weather forecasting that could be beneficial for the physical models is in data simulation. So the data simulation has this problem of the data that the errors should be uncorrelated to have an impact. And AI could be incredibly beneficial in subsetting the data and having the data that are most impactful to get fed into the deterministic or the physically based model. So I would like you all to comment based on your different perspective of how do you envision the future of weather forecasting, whether you think that AI would replace physical models or not, or if you think that the hybrid approach should be more convenient. So I'll stop here.
Okay, yeah, it's a great question. You're definitely speaking the language that I speak to my colleagues on a day-to-day basis. So I hope it doesn't, I guess, get too into the weeds for the broader audience here. So I'll try to generalize, but there are a lot of fundamental questions that are being asked with these AI models and where they're going to go and how they will change weather forecasting and how we treat observations, how we make predictions. My microphone go off. Okay, so I think that there's a couple of things. One is that the way that ECMWF at least is currently operationalized, they still require a traditional data assimilation approach, which uses physics. Now, there are groups, including ECMWF, that are trying to go beyond this and even replace that with AI, and there's a few different methods for doing that. The question I always come back to is that, can we go to higher resolution than we currently have in training data sets? Can we use new and novel observations effectively if we don't have a historical record to train these AI models on? Can AI tell us what the next generation of satellites should look like based on what will impact them most, or is that something we still have to go back to physics for? And I don't have the answers to all these questions. I think those are kind of the fundamental questions that both the public and private sector need to start thinking about, because unlike AI models, it takes a little bit more time to build and design satellites far into the future, and they might be dealing with a very different world than they currently were. The current generation is designed for.
So we've thought a lot about this physics, AI boundaries and combinations in the flood space. I'm not going to answer so much for the weather space because that's a little bit outside of my area of knowledge. But I think if I had to give one lesson, it's this: that question is really domain specific. So what I see happening a lot in my own sort of subfield is people doing a lot of research, trying to figure out how to bring in the knowledge of the system that we learned about in grad school, that we've been building models on for years, how to bring that into this sort of new paradigm and understand ways that we can extract information from that subset of knowledge and those equations, also from data, and bring them and add them together. One thing that I think that we could work on in that around those sorts of questions is understanding where the information content comes from for a given problem. And that's really going to be problem dependent. So let's take hydrology, which is my field, as an example. A lot of the physics, quote unquote physics, are more like the physics wrapper around a weather forecast model and less like the dynamical core, right? And so in our case, we've spent years exploring this question, and every time we've asked this question, the empirical answer has been, in hydrology, remove the physics. And that's really because just the way that these our problems work. And we've even seen in extreme events, the physics-based models saturate much more quickly than the AI-based models. Now, I don't believe that's true everywhere. And certainly in climate, the fundamental question in climate AI is, can the models learn the migration of attractors in phase space from the data? And can those migration patterns be extrapolated reliably, right? And so we don't know the answer to these questions. One of the things that I would like to see more of happening in the world are experiments set up to test these types of questions. And just to be clear, it would involve building an entirely new climate model, and not an AI climate model, and not a physics climate model, but a model that is specifically designed to allow you to test these hypotheses, ask questions about where you're getting information from physics equations and where you're getting information from data, and to be able to sort of move these pieces around. But I think these are really the core of the questions that we have to ask when we talk about reliability. And I do think it's domain dependent.
It's a. Oh. Microphone? Thank you. It's a fun and fast-moving field. I think there is, so benchmarking. Let's say community builds an AI model for weather forecasting. What do you compare it to? Well, what is the state of the art? It's a physics-based model. So a comparison is made, and I think that's where there's this misunderstanding of it's in competition with, it will replace once it's better. I think it's simply just that is the benchmark. We did quite a bit of work with Environment Canada, Environment and Climate Change Canada, their weather forecasting group, helping bring in AI tools, not replacing their weather forecasting model with an AI emulator, but instead tools for post-processing, etc. We always came up against their forecasters saying, you're going to replace us and everything else with AI. And I just don't think that's true. It will become part of it. There's a nice model that was built, I think it was a Google and MIT group called Neural GCM, which has a great combination of physics being retained in the dynamical core and then machine learning elsewhere. And so to me, that seems to be a template for going forward. But like I said, it's a fast moving field, and I think it's difficult to predict exactly where we'll go. But no, it'll never be only AI.
Great points. I think we have time for at least one more question. In front.
So this is going to be a variant on the first question. It's great to hear from several of you that are working in the private sector doing these data analytics and even filling in gaps in data and actually collection of data. We also heard you talk about the importance of the public sector data that's provided by NASA and NOAA. So unfortunately, we're in a political environment where the value of anything that the public sector does is not being touted very much right now. So looking to the future where there's probably more and more private enterprise doing some of the work that you're talking about, how do we talk about what the role of the government in, where does the government still need to be there to collect certain data sets or provide core capabilities that would allow the private sector to do more with this data and expand this in the future?
That is a great question. It's very much a policy question. No. I have some thoughts on that, but I don't know if you would want to opine first. Oh,
Can I borrow the mic?
Yeah.
This is the only one left. Yes, this is a question that I've heard before in recent months. And I think both with myself and as a company, we can say that we absolutely do not see ourselves replacing the public sector measurements. There's a very nice synergy with the way things currently are, where we provide some complement on top, and hopefully we can demonstrate that we can do things and scale up measurements in a way that the private sector is more efficient. But it all relies on some fundamental R&D, like development of component technologies that was happening and being sponsored by NASA 10 and 15 years ago. That the private sector, I know, like the investors are not willing to take on that level of the risk. We need something with a higher TRL. So I think that there's still incredibly incredible importance for these programs, and we can't succeed for long unless they continue. So, and I think it's also important that, it's some fundamental backbone capability, again, because of the trustworthiness, end-to-end calibration, knowledge and stability are still required, I think, and that needs to be done by a government entity that has the broad trust.
Yeah, maybe I'll combine this with an answer to. So let me combine this with another answer to Dahlia's question about authoritativeness. We started off this project that we're doing at Google and Climate AI really to provide information to our users. I think it'd be fair to say, I'm not sure that everybody in my company would agree, but I think it would be fair to say that we'd rather collect this information from governments. And one of the reasons for that is that when you're talking about things that affect human beings, you want there to be an authoritative source. You want there to be one voice. It's the single voice principle is what we call it. And it's really important that there's some authority that has this the public interest at heart as the first principle. So the role that we would really like to play is to do some of the research that's more on the applied end of the spectrum. We always have to be thinking about the users and always have to be thinking about the people. We're not doing basic science. With very few exceptions, we're not looking at new sensor technologies. We're not out in the field deploying sensors. We're doing things that help take the data that's available and move it into information for users. So we can play a role, and one role that we really like to play is to privatize some of the high-risk research on the applied end of the spectrum, where we can make a case that this is useful to individuals. But then when that research is done and we've kind of proved that it can work and we've kind of extracted some of the AI insights out of that and some of the kind of stuff that we care about, we really need to go back into the space where there's an authoritative voice and some type of government oversight, because when people act, they have to act in a way that's socially responsible. We can't have 17 private companies coming out and giving 17 different instructions to people. And so there has to be some level of coordination. And one of the things that I'd like to see going forward is a better or a more robust or a working roadmap between public-private engagement in this sector.
I echo everything that was said. We've been really fortunate to have fantastic partners in NASA and NASA Impact especially, who are willing to go down, I think, what was a relatively high risk, high reward project. We're now at a point that we have learned a huge amount about how to build these models and how to make them usable. And I'm not sure where this investment would have come from originally. So I think together we made things better. One of the reasons it works so well is IBM Research, our group, we have a lot of strong AI scientists and AI engineers. NASA has a lot of very strong domain scientists who understand not only the data, but also the processes that need to be captured by these models. It's working together has allowed us to, I think, do something that is quite important.
That's excellent. Thank you for the questions. We're about out of time here. And I think everything I would have said, they've hit really well, particularly the risk, as I put on my MBA hat. Yeah, most companies don't want to take on the risk of something that NASA can do. And can I just get a quick round of applause for our panelists? They've been excellent. Thanks for letting us be here, and enjoy the rest of the conference.